Swayam Prabha. Digital India. Educated India.
Yeah, we said that we will start with the lectures on lateral dynamics. And we were talking about, as a precursor, when we started this in last class, we were talking about what we called as high side fall. Okay, we said that there is the graph and both of them are acting. I hope you were able to derive the expressions which we wrote in the last class. If there are any questions, we'll answer that in the tutorial class, right? And please derive those expressions which we said or which we gave, which we saw in terms of the combined slip, okay? The lateral and the longitudinal slip from the brush model, right? Try it out, or else we will do that sometime next week in the tutorial class, right? Okay. So we were just talking about this as a precursor to the lateral dynamics. We said that suppose a motorcycle is taking a turn. You're taking a turn in a motorcycle, and that you are applying a brake. Okay, when you apply the brake, actually, what are you doing? You are getting both the longitudinal forces. You require longitudinal forces for braking, as well as due to cornering, you also require a lateral force. Assume that you are at the edge of the friction circle or ellipse, as you can call it. Or in other words, you are, say, at this position. Let's say that you are at that position. In other words, you are making use of all the friction that's available, right? Suppose you let go the brake that you have applied, okay, and you keep cornering. What would happen? That's the question. Suppose you let go the brake and then you continue your cornering. In other words, what would happen now? The longitudinal force goes to 0, right? The longitudinal force goes to 0, and suddenly, okay, you are now shifting from this corner where you are at the boundary to the vertical axis, okay, with the same force, total force. You are now shifting from here to here. In other words, the lateral force is more than what is required for the equilibrium of the vehicle.
So, why would the total force remain constant? I understand
Yeah.
that the lateral force would remain the same, but
Yeah, because what happens is something like this. I've plotted the slip curves. See, suppose you are at this point, okay? You are at this point. Then if you now apply a brake, the slip force remains the same. In other words, you are moving from here. These are the slip curves, forces that are generated due to the slip angle. The slip angle remains the same, okay? But you are shifting from this corner onto the y-axis. So in other words, you are shifting from B to C. You are shifting from B to C position, right? So because look at these curves, how they are. This is the lateral force curve. Maybe this is equal to alpha is equal to 3 degrees and so on, right? So you are shifting now to the y-axis. In other words, the forces, the y-axis force which was this much has suddenly increased from this point to that point, right? So when the forces increase, suddenly increase, and is not is more than what need to be compensated by the for the centripetal force, then there is no equilibrium, there is loss of equilibrium. So in other words, you overturn. Clear? Okay. We'll come back to this maybe towards the end of this lateral dynamics, so you understand it better. But I'm only telling you that there are practical applications of what we're going to study. Okay. Now we will get into the complete lateral dynamics derivations, so that when I come back, you would understand this better. Right. Let's look at how we are going to deal with lateral dynamics. Let's go into some fundamentals of dynamics. Right? Now I'm going to deal with what is called as a body-centered coordinate of a vehicle. I'm going to deal with what is called as the body-centered coordinate of the vehicle. In other words, you can study the vehicle motion with respect to what is called as the inertial frame of reference, which I would put in terms of capital X and capital Y, or you can study this motion with a body-centered coordinates, which I would put as X and Y. It is a usual practice to study the motion of a vehicle in terms of body-centered coordinates rather than the inertial frame of reference. You all have done engineering mechanics, so you would understand what would happen when I have a body-centered coordinate. You would see that you have to have additional terms to take care of the realignment of the body-centered coordinates. In order to take care of realignment of the body-centered coordinates. In other words, the body-centered coordinate, what are the body-centered coordinates? Suppose this is the vehicle. So I have a body-centered coordinate in this vehicle. So the vehicle takes a turn, the body-centered coordinate also takes a turn. Okay? So they also move along with the vehicle. In other words, I have to take into account this motion of the vehicle and the body-centered coordinates. Right? How do we take this into account? First thing is, that's what we are going to see. And then we are going to apply Newton-Euler equation in order to understand the motion. Right? Let us say that the usual ijk is what defines the unit vectors along x, y, and z. Right? And let's say that the velocity of the vehicle in the three directions are u, v, and w. These are the three velocity of the vehicle in the three directions, right? And let's say that the rotation, okay, which we would call as P, Q, and R, denotes the rotation of the vehicle, or in other words, the angular rotation velocity or angular velocity of the vehicle. Okay, so this is the angular velocity, rotational velocity, and UVW is the linear velocity of the vehicle. In simple terms, what is P? P is nothing but the roll, Q is the pitch, and R is the yaw of the vehicle. Okay? So we call this as P, Q, and R. Now, what are the peculiarities if I am going to deal with this kind of systems? Okay? That is what we are going to see. You know, like what are the additional terms that come into picture? Let's say that the force acting, okay, on the vehicle, let me write down the forces as Fx I plus Fyj plus Fzk. There's the three forces that are acting on the vehicle, and the moment m, or let me call that as tau. Okay, the moment that is acting at when they are all vector quantities, I am putting a squiggle at the bottom to indicate that they are vector quantities. So let me call that as L plus, I'll maintain the same thing, so M plus N. What am I going to do? I'm going to first write down the linear momentum and the angular momentum, and I'm going to look at the rate of change of this momentum, and the result is the Newton-Euler equation. Right? That's all I'm going to do. So let me write down first the linear momentum. P mv, and the angular momentum, let me call that as h. What is angular momentum? I omega. Right? Now what is I now in this case? The moment of inertia, it's actually a matrix. Right? So you actually have this as I. Okay? Omega, what are omegas? Angular velocities. How have we defined this? PQR. Okay? So I omega. And what is I? I is, if you want, we can replace that with the matrix notation. Okay? You would have studied this as one single quantity along xx and so on. Now we are just extending this to 3D. So I'm writing this as a matrix, and so Ixx. So this is Ixx, Ixy, Ixz, Iyy, and so on. Right? So all of you know the definition for Ixx, integral y squared plus z squared dm, right? So you know the definition for Ixx. Throughout the volume of the body, and you know also what is Ixy minus of integral xy dm, right? Okay. From this, we go to write the, we're going to have some peculiarities, we'll come to that in a minute. We go to write the Newton-Euler equation, right? So what does the Newton-Euler equation say? So how do I, if it is just F is equal to ma, we call this as a Newton's equation. So if it's a Newton-Euler equation, we also include the moment that is acting, okay, on the body. So we write F is equal to, where P is the linear momentum of the body. Similarly, we write tau is equal to the rate of change of angular momentum, right? So far it's very simple dynamics. Now we have to be careful in writing these terms, okay? We are going to write it with respect to the body-centered coordinates. IJK, I've introduced that for the body-centered coordinates, okay? Now I have to introduce them with respect to body-centered coordinates. Let us see how, for a body-centered coordinates, a particular vector changes. That's what is our goal now. Okay, let us consider a vector A. Okay, vector A, some vector A. We are following Carnap. The reference for this is vehicle stability by Carnap, CVSTRNOPP, Karnaugh vehicle stability is the reference for this. So let's say that I have a vector A which I am going to express in terms of ijk, which are the unit vectors in the body-centered coordinates. Right? I want to find out now the variation or rate of change of A. So in other words, if I now write dA by dt, I write this as A dot xi plus A dot yj. A can be any vector. It can be velocity. We'll see that. A is a dot k plus, because I is not the inertial frame of reference and I also changes with time, so I have to rewrite that part. So I'll, in other words, okay. Clear? All of you from fundamental dynamics know how to write I dot. How do I write I dot? I dot, j dot, and k dot. In other words, di by dt. You remember that in your earlier classes, you would have done this. Suppose I have x and y along which I and j are defined, and if it is rotating with, say, for example, omega, so the new coordinate due to a rotation of an angle theta gives you x prime and y prime, right? So the new value of I, which, let's say that I prime, which is equal to I plus di by dt, right, is given by the changes, okay, here, which is along j, same way along I, okay. And so what is di by dt? D theta by dt into j, right? So because this is a unit vector, I is a unit vector, r into theta gives me this, right? So this is r into theta. It is along the direction of j. So di by dt, di is this, di by dt is nothing but d theta by dt, d theta by dt is omega into, say, j, right? So this you can do it for all three and write down this part. Oh, yeah, right. This we will keep that plus omega cross A. That's what happens. Omega in our case is P, Q, and R. Clear? So we will call this part, we'll give a new name to this, and we will call this as dou A by dou T. Call this as relative. So what is the physical meaning of the first term? The physical meaning of the first term is simply that that's what an observer who's sitting in the body-centered coordinate would see as the rate of change of A. Right? So because I have to apply this, my formulas in terms of inertial frame of reference, now I know that when the body-centered coordinates, okay, changes with time, okay, I take into account that as well by putting that omega cross A. right? Okay, what is omega cross A? All of you know this, where omega cross A, how do I write that? I, J, K, what is omega? As I said before, PQR, and A is AX, AY, AZ. Right? Okay. So now dA by dt, if you write that in terms of this, write it in terms of that. So what would happen for I, A dot x plus, pick that up from there, plus I into QAZ minus R AY. The whole thing is I, right? Clear? If I want to express this as a vector, then I would remove that I and just write that as a vector, because after all, A, that's a vector. Write down A dot y plus, what are the terms that are there? That is for the j term. RA x minus P into AZ. And A dot Z plus PAY minus QAX. Yeah. So that is dA by dt. Okay. Now I can apply my Newton-Euler equation by assuming that A is, or substituting for A the velocity. I can write down the first of the equations, which is dP by, that is here, that equation I can write it down. Of course, m is a constant, so m is, you can take that out, and so write down what is the first of the equations. Simple. Fx, Fy, Fz is equal to, the first term becomes, so m into, what's it? U dot plus Q into UVW is what we said, Q into W minus R into V. Right? Any questions? No questions? Everything is crystal clear? Okay. Write down the rest of it. Write down the rest of it. V dot plus R into U minus P W and W dot plus PV minus QU. Right? Okay. So that's the first set of equations. The second set is my tau is equal to dH by dt, which is here. Tau is given by L, M, and N. So that becomes my left-hand side. So let's write down that. So tau is equal to dH by dt. Again, that is equal to dou h by dou t relative. This is the first term. That is the h dot term plus omega cross h. Remember, h is equal to, h is equal to I into P, Q, R. So omega is P, Q, and R, right? Omega is not P dot, Q dot, and R dot. It's not P, Q, and R, right? This is a very standard terminology. For example, R, small r, is used in the literature in vehicle dynamics to indicate yaw. Okay, this is a very standard terminology. It's not usually written as omega x, omega y, and omega z. Right? Write down that. That's going to be an interesting expression. It's going to be a long expression. Don't differentiate I with respect of course t. So what's the first thing? Okay, let me remove this so that you know that already. L, M, N. Okay. IXX P dot plus IXY Q dot plus IXZ R dot. That's the first term in the vector, plus write down omega cross H. Right? Okay, I'll write down the final things. It's just nothing. It's not very difficult. So I'll quickly write down that. I hope I don't make any mistakes in this. If there's anything, just point out IYY Q dot plus IYZ R dot. And IZX P dot plus IZY Q dot plus IZZ R dot. Okay. So that are the dou h by dou t terms. So then I have to put the same way Q into AZ minus R into AY. Okay, what is AZ? AZ is HZ. HZ is what? Remember that I had to multiply, I had written already what is H. So IXX, IYY, IYZ, multiply it and put that there. And so there will be plus Q into HZ. Okay, how many terms would be there on HZ or HZ? How many terms? There will be 3 terms, right? So write down those 3 terms. So you can write down that as Q into HZ minus R into HY. Remember, that hx, hy, hz is what? Ixx p plus Ixy q plus Ixz r, right? So what is this term? Is the hx term, and that term, hy term, hy, and that term is the hz term, right? So that is what is going to come here, and so on. Though the expression looks very formidable and long, it's very simple to understand. There's nothing much. It's very simple to understand this expression. Okay. Don't worry, I'm not going to deal with this kind of huge expression. I'm going to make, as usual, some assumptions. Right? What are the assumptions you think we can make? What are the terms I don't like? Yeah, okay. But I want all that, let's U, V, W terms I need. The terms usually I don't like are these I, X, Y, and so on, right? So how do I eliminate that? Look at it, imagine that you have a car. Up to this is mundane. There's nothing great about it, just the relationship between the inertial frame of reference and body-centered coordinates. Now, what are the assumptions you think you can make? Symmetry, fantastic. So symmetry in a car is about what are the axes that you can consider the symmetry. What do you think we can consider? Yeah. So one is the longitudinal axis. You can consider this as symmetry. The other is that we are dealing with principal axes. Let's say that the Ixx, okay, Iyy and Izz, and so on, what you have chosen as X, Y, and Z for the car, let us say that it is the principal axis. Are they? May not. But then in that case, if you choose them to be the principal axis, all others go out. Right? Okay. So we make this kind of assumptions, and we also say that the Q, the pitch, is not of interest to us, neglect it, and ultimately we will bring it down in a very simple, handleable form. Right? We're going to make all these assumptions, and then we'll bring it to a handleable form. So what is my first expression? I am going to now write down, right? Is this is clear? Any questions? Okay. Now, with that assumptions, I'm going to rewrite my expression 1, say like here, 1, and my expression 2. Substitute that and write it. Going to be a huge expression. And I'm going to rewrite them in simple form, handleable form, which I'm going to use. Clear? Okay. So let's see. Write down what is the expression which I can use. Fx and Fy. Let's write down Fx and Fy. So Fx, that is the longitudinal force in the longitudinal direction, which we had already seen, okay? But with respect to the body-centered coordinate, is m into u dot minus rv, right? So that's the body-centered coordinate expression for longitudinal forces. Now write down for the lateral force, Fy is equal to m into v dot. Okay, that's the first term, our relative dA, dou A by dou T. So because of which I get a v dot term. What's the next term I would get? I'm neglecting q and so on, plus r q. Right? And what is my L and M? L and M from my expressions here. So it will be, the first term will be there, Ixx into P dot. If you are not considering it, just consider symmetry, you're not considering that you are in the principal axis, then Ixz will be there. So Ixz into Z into R, okay, and so on, right? So you can write down for M R dot again plus the last is this term. What we have is here. The other terms, because of symmetry, goes off, plus Izx into P. Okay, so I'm going to remove these two later and look at, I would say, the expressions for the lateral dynamics. So this, in other words, this is the most general expression you can look at for the three-dimensional case. But I'm going to, from here, I'm going to make geometric assumptions so that ultimately the equations I'm going to use become handleable. Right? That is what I'm going to do. And from this handleable equations, handleable in the sense that, I want to work it out in an analytical fashion, I want to look at the results, I want to interpret it, and so on. So from this, I'm going to extract out the equations for lateral dynamics. That's all I'm going to do. Clear? Any questions? Yeah.
M, how did you write Izx? For M, that's for M.
Oh, sorry. N. L, N. Okay. For M, you can, yeah, right. Sorry. N. You're right. And that would be, okay, that's the first, that's this term. And you can write this down. I think you should have Izx into P. Yeah, you're right. Good. Okay. Now we will move and be more specific, and we will get into the expressions for the longitudinal dynamics. So what are the two expressions of interest to us in longitudinal dynamics? What are the two expressions which are of interest to us? When we are talking about, lateral dynamics. When we're talking about lateral dynamics, what's the force? Talking about Fy. Right? And what is the other thing that we are talking about? Is the moment due to lateral forces. So the moment due to lateral forces will be along z direction, right? The moment due to the lateral forces will be along z direction, so that is my interest. Right? So in other words, just to quickly summarize, so I have forces that are acting, okay, that's the vehicle. Then that forces create a moment, okay, which is perpendicular to the plane of the board, which is the z. So the two equations of interest to us are the lateral forces and the moment that is acting due to the lateral force, which is this. Yes. No, yeah, we will come to that. Okay. So we are now going to look at a simple model which is called as the bicycle model. Okay. So when I consider this, that's why I've drawn it like this. I am not going to consider the roll. Okay. So you're absolutely right. I have to, roll is an important phenomena that happens, during cornering. But right now, okay, I'm going to neglect the roll. I was expecting that question. I'm happy that you asked this. So let us now look at these two expressions. In other words, what I'm going to do is I'm going to shrink these two wheels, okay, into one wheel like this, the front and the rear wheels, and look at the vehicle by means of these two wheels, the front and the rear, and call this as a bicycle model. This is one of the most famous models in vehicle dynamics. As he very correctly said, we are not taking into account the roll right now. But then, after we study this, we are going to introduce complexities one by one in order to understand what happens, okay, because of other factors which we have neglected. What happens due to the other factors? This is what we are going to study. Clear? Okay. So we are into one of the most important models in the whole of vehicle dynamics, which is called as the bicycle model, right? So I'll remove this. As I promised, I'll make it much easier. So that's the one equation. I'll remove this, and these are the two equations that I'm going to look at. Okay. Let me now expand this bicycle model. Now we'll introduce, after crossing all these equations, now we'll introduce a lot more again physics. Right? Okay. So let's say that this is the rear wheel which I've collapsed. And let's say that this is the front wheel, which is, okay, I'm giving a turn to the front wheel. Let's say that that's nothing. I'm just exaggerating this. I'm giving a steering input to the wheel. Okay, of course, that's the vehicle. That's the center of gravity location of the vehicle. Okay, so that is the lambda which I had given, which is the steering input. Now, so I'm taking a turn. When I take a turn, I will of course need this Fy which we have been talking about, right? And how is Fy created, or how is it generated? We have already seen that this is due to the slip angle. So a slip angle, if this is the force that's acting, okay, there are small angle differences which I'm going to neglect, right? So that's the Fy in the front, and this is the Fy at the rear. So how is it generated? By slip angle. And what is the slip angle? And that is the slip angle. Okay. Slip angle is alpha. Okay. Note out my coordinate system, that is x, y, z is perpendicular to the plane of the board. Clear? Right. Now, the very first point I want you to notice, we will continue this in the next class, is that the slip angle, which we have seen it before, but I'm going to put some sign to it. The slip angle is, look at that, is in this direction, which is in the negative direction, okay? And the force is created in the positive direction of y, in the positive direction, okay? So this negative and positive directions, we have to, though we know this physically, we know how Fy is created, but this negative and the positive directions, we'll be careful when we write down the equations, right? So there will be two alphas that are created, because I want the front and the rear, and let me call that as the rear alpha, or alpha r, the rear slip angle, and let me call this as the front slip angle. So note that there is a confusion. I have said this again and again. Note that what is slip angle, this alpha, is nothing to do with this delta, which is the steering angle. Clear? I need a slip angle to generate the force. Now, I have these two equations. Okay. And the n is equal to r. What's r? That's r, okay, which is the yaw velocity, and r dot is the rate of change of r, right? Okay. Let me call, this is again usually done like that. We call this as L1 and L2. Let me call that as A and B, because in the lateral dynamics literature, the distance from the of the CG location from the center of the tire is A, and that's B, right? Okay. So that A into FYF minus B into FYR is the moment that is acting. So N is equal to FYF into A minus FIR into B, which is equal to IZZ R dot. Clear? Right. Fy, we'll come to this in a minute. Fy is FYF plus FYR. Right? Okay. We'll continue this in the next class. We'll stop here and we'll continue the bicycle model. This is probably the most important central piece of the whole lateral dynamics. So we'll look at this very carefully and then understand the vehicle behavior during cornering. So we'll continue in the next class.